Hello, everybody, and welcome back to BioSC 140 Human Physiology. This is Laboratory 2. This is on Lab Quiz 1. So this is Lab Quiz 1 material. I want to point something else out before we get started. So as you can see on this first slide, there are 5 labs within this one lab. So this is Laboratory Day 2. But there's FOX 1.3a, FOX 1.3b. There's also FOX 8.4a, FOX 8.4c, FOX 8.4b. In the lab supplement, you'll find all of this under Laboratory 2. In the FOX book, the lab manual, you'll find FOX 1.3a, under FOX 1.3a, a section 1.3a. You'll find FOX 1.3b in section 1.3b of the FOX book, and so on. I want to point something else out. These 5 experiments play a little bit larger of a role than most in this class because of the JALR assignments and your laboratory report. For those assignments, the JALR assignments and the laboratory report, it asks you to choose one experiment from within Laboratory 2 to use as your model experiment. You use it as your model experiment for JARL 1, 2, 3, 4, and 5. And then for the laboratory write-up, you will write up this experiment as if it was your experiment for a scientific research paper or a scientific research journal. So introduction, methods, results, data, and so on. Now, I want to be clear. It's best if you pick one experiment out of these 5 and you use that one experiment for all of the JARLs and the laboratory report. Because the JALRs will prepare you for the laboratory report. You're going to have half of your laboratory report already written if you use the same lab for all the JARLs and the laboratory report. So pick, 1.3a, or pick 8.4a, or pick 8.4c, and run with that one for the rest of the semester. I recommend watching this video, reading over the labs, and then moving on from there. Once you've become familiar with each of the individual labs within Laboratory 2, then pick which one you want to go a little more in depth into and run with for the JARL assignments and so on. And with that, let's get into it. So these slides, let me actually give you a little more background information. So these slides were prepared for the in-person labs. I've been using variations of these slides for 8 semesters now. This is my 8th semester. Normally, we have a 3-hour lab 2 days a week. We meet in the laboratory and I go through the first section of these slides. These slides are broken up into 2 sections. The first section is what we're going to do in lab. It's how to do the experiments. It's what we're going to do in lab. Then after I've gone over the first section of what we're going to do, we go and we do the experiments in lab. Then after we're all completed doing the experiment, we come back and we do what I call the discussion. We do the second section of the slides, which goes into the theories, the science behind each of these labs. So part 1 is what we're doing for each experiment and how we get the data. Part 2 is analyzing that data and the background science. In the slides, they will be like the split between the first half and the second half will be a large slide that says discussion, because the discussion is what I call the second half. Because we're online asynchronously, we will not be actually mixing chemicals and looking through microscopes and putting electrodes in frogs and all that fun stuff. But, you know, we're still going to talk through the experiments for the first half. I think it's important that students know what we did for each experiment, as in how did we gather the data. I will ask questions on the quizzes and on checkups regarding how we did the experiments and how we got the data. So definitely pay attention and definitely understand each, how we did each experiment. Generally, you don't need to know we mixed 3.42 milliliters of water. You don't need to know like the numbers, but be able to tell the general story of what we did for each experiment. And then definitely be, you know, familiar with the discussion and analysis of the data and the theory behind it. All right. Well, with that being said, let's get to it. So FOX 1.3a is the water bath experiment. So this one works well as a thought experiment. So I think most students are familiar with what a water bath is, but for those of you who need a refresher or are not sure, a water bath looks like this thing over here. Let me, 1 second, I gotta get my, get it up. All right, a water bath looks like this object on the left side of the screen. What it is it's a container for water. And on this dial in front of that container, you say, container, I want you to keep this water at this temperature. I want you to keep this water at 50 degrees Celsius. So that's what we're doing in this experiment. We're putting water inside the water bath and we're saying, hey, water bath, keep this water at 50 degrees Celsius. We're then gonna record the temperature. We have a thermometer that we put in, and we're gonna record the temperature every minute for 5 minutes. And what we're gonna find is that the temperature is 50 degrees, 50 degrees, 50 degrees, 50 degrees each time. After those 5 minutes, we're going to put a large amount of ice inside the water bath. A large amount of ice inside the water bath. Think about what's going to happen to the water temperature when we put the large amount of ice inside the bath. So most students understand that if you put a large amount of ice, or you can visualize it, it's pretty easy, yes. You can visualize that if you put a large amount of ice inside this water bath, the temperature of the water is going to drop. Right when we put the ice in the bath, we're going to start measuring the temperature of the water in the bath every 15 minutes or so for the next couple hours. We expect to see a large drop right when we put the ice in the temperature. Now, thought experiment. What's going to happen to the temperature over time? As we monitor the temperature after putting ice in the bath, what's going to happen to the temperature? The temperature was stable at 50 degrees Celsius. We put a large amount of ice in, and then we measured the temperature every 15 minutes for the next couple hours. What's going to happen to the temperature? All right, so we'll get back to this when we do the discussion part. Here's something else to think about. How well does the water bath mimic human homeostatic control of body temperature? Little heads up. Oh, 1 second, I need to. Little heads up. Homeostasis, homeostatic control. Homeostasis is the maintenance of a stable internal environment. So our bodies have an ideal temperature. Homeostatic controls helps us maintain that temperature. So how well does this water bath mimic human homeostatic control? What elements of a homeostatic control system does this water bath exhibit or lack? That's where we're going to be going in the discussion part. Next up, FOX 1.3b. What we're going to do in this one, we can actually do together through Zoom. So normally, what we do is we break into small groups. There's 4 or 5 people in each group, and we take each other's pulse rates. You can take your own pulse at home. The best way to do it, find your thumb, take a couple fingers that are not your thumb, and feel for your radial pulse kind of right in this area. You can put your finger on the bone, kind of slide it inward, and you should be able to find a pulse right there. There's many ways you can find a pulse rate though. You know, the neck one is popular also. You can also use like a pulse oximeter, or a lot of people now have watches that tell them their pulse rate. What you should do is count how many beats there are in 15 seconds. Write that down in trial 1, multiply it by 4 so you get beats per minute, and you'll have your beats per minute. Do that 5 times, and then average out each one, average them all together to get your average resting time. Normally, we would do this in our groups for each person within the group. Then up on the board, we would have 2 columns. We'd have a column on the left and a column on the right. And the 2 columns on the left, it would be people who regularly exercise. And on the right, it would be people who do not usually exercise. So exercisers and non-exercisers. And students will self-declare if they consider themselves an exerciser or not an exerciser. So you can put yourself in each column, just whichever one you feel that you fit in. Then there would be rows. Rows for different heart rate ranges. So 90 to 99, 80 to 89, 70 to 79, 60 to 69, and so on. And so students, after they come up with their resting heart rate, would go put a hash mark, a tally mark, in whichever category they are in. Do you think, this is what I'm going to leave you with, kind of the thought where we're going with this for the discussion. Do you think that the resting heart rate on average is higher for exercisers or non-exercisers? Do you think that the resting heart rate on average is lower for exercisers or non-exercisers? That's where we're going. Next up is FOX 8.4a. So this one is an example of an experiment where the lab supplement and the FOX, we changed the protocols a little bit. The supplement will have the protocols, the exact amount of water and such that we would use if this was a live class. So here's our setup. In this experiment, we're going to set up, let's see, 1, 2, 3, 4, 5, 6 beakers with fresh water, and we're going to measure their pHs. 6 beakers with fresh water, we're going to measure their pHs. pH of fresh water, remember pH is a measurement of hydrogen ion concentration. Hydrogen ions are protons. How many H pluses? What is the concentration of H plus floating around in the solution? In fresh water, provided it's perfect, in an ideal situation. Now, it's hard to make ideal situations in labs, but if it was an ideal situation, the pH would be 7.0, right on the dot. In 2 of the beakers, we're going to add 1 drop of HCl. So let's do this experiment. We have our beakers in front of us. We have our pH meters. The The pH meter is saying 7.0, and we add 1 drop of HCl into that beaker. That hydrogen and the chlorine are going to separate, and that hydrogen ion is going to increase the concentration of hydrogen ions in the water solution, which is going to increase the pH. We should see a fairly dramatic pH increase when we add 1 drop of HCl. So if 7.0 right here is fresh water, we add in 1 drop of HCl, and we're down at 5.5 pH, or 6, somewhere around there. We then add in 3 drops of HCl, or 2 more drops of HCl for a total of 3, and it drops it down pretty far, usually around the 4 range. We're then going to take another one of our freshwater beakers. We're going to add 1 drop of NaOH and measure the pH. So NaOH, the Na and the OH are going to dissociate. This OH right here is going to grab on and hold on to hydrogen ions that are in the solution. So it's going to actually take hydrogen ions out of the solution. It's going to lower the concentration of it. So it's base, and it's going to raise the pH actually, make it more basic. So it's pretty much the same thing as this, just in the opposite direction. We go from 7 to 8, and then with 3 more drops, we go from 8 to 9 or 10, somewhere around there. We're then going to do the second half of this experiment, where it's the same experiment. The one thing that we change is, instead of using pure fresh water, we're using a buffer. What do buffer solutions do? Think back to chemistry. What do buffer solutions do? How would this experiment be different if we used a buffer solution and added HCl or NaOH to that buffer solution? Well, the data-wise, this is usually around 7 to begin, or this is 7 to begin with. You have 1 drop, and we're at 7 still, or 6.9. Then we add 3 drops, and we're at, usually in lab, like 6.7, usually still pretty close to 7. With the NaOH, we pretty much see the same thing, just in the opposite direction, in the basic direction. Why is that? Next up, we have Fox 8.4c, the role of CO2 in respirations. The role of CO2 in respirations. So measure breathing rate. So in this experiment, we're in our groups, and we measure the breathing rate of some members of our group. There's a few ways that you can measure breathing rates. Typically, this first one, watch clavicles. People generally don't like you staring at their clavicles, so I tell students not to do that. But that is done sometimes. I know a lot of you want to be nurses. Sometimes when you're doing your rounds in the hospital and you want to see if somebody's sleeping, somebody might be sleeping in their room and you want to make sure they're still breathing. Looking at their clavicles, seeing if there's chest excursion, chest expansion, which would be indicative of a person breathing. That's a good idea. But when your patient's in front of you, they're not sleeping, they're awake, staring at their clavicles generally isn't a good way to measure their breathing rate. So just placing a hand on their back or placing a hand on their shoulder, you can feel their chest expand and contract, and that's how we take respirations in class. Count for 30 seconds, then multiply by 2, and you'll get your respiration rate over 1 minute. After we have our resting respiration rate, we have the student, the person who just measured their respiratory rate, take 4 or 5 deep, rapid breaths. Please don't do this to the point where you faint. Safety, even on Zoom, is #1 priority. Don't do this if you're gonna faint. Please don't. So what do I mean by deep, rapid breaths? Let me demonstrate. Right after they're done doing that, we're then going to remeasure their respiratory rate. how do you think the person's respiratory rate is going to change after 4 or 5 deep rapid breaths? That's what we want to find out with this experiment. And next up, Fox 8.4b, the effects of exercise on CO2 production. So usually we do this one last in class. And we have each group get 2 beakers. You add 100 milliliters of water into 1 beaker. You then add 2 milliliters of a 0.1 molar NaOH into that 1 beaker with 100 milliliters of water. You then split that, before you split it, you add 1 or 2 drops of phenolphthalein. Phenolphthalein at some pHs is pink, and phenolphthalein at other pHs is clear. At a basic pH, the one where, we added NaOH, so at the pH where we start in this experiment, phenolphthalein is going to be pink. Phenolphthalein, if it's in a more acidic solution, will be clear. So we're going to add the phenolphthalein, mix, and then split that phenolphthalein basic solution into 2 beakers. We're then going to have some straws, and we're going to choose 1 student, and we're going to have that student breathe and exhale into straw. Breathe and exhale through the straw into the solution until that solution turns clear. Until that solution turns clear. So I'm going to give you a little heads up. When you exhale, what do you exhale? When you exhale CO2. CO2, when it dissolves in water, turns the water more acidic. So, the more carbon dioxide we exhale, the more acid's going to be absorbed into the solution, the more acidic the solution's going to be. Eventually, that solution's going to become so acidic that the phenolphthalein goes from a pink color to a clear color. Now, after we've measured the time it takes for that student to, exhale and turn the phenolphthalein solution clear, we're going to have them exercise for 1 to 2 minutes, enough to get them breathing a little heavier. And then we're going to do it with the other solution. So, hypothesize, do you think the phenolphthalein solution is going to change color faster before the person exercises or after the person exercises? So hypothesize, we'll talk about that in the discussion. Here's an overview of what we're doing for this section, and I'm going to stop the video here, and I'll shoot another video for the discussion. All right, talk to you guys soon.